Howdy, hackers, and welcome to another episode of FairLight TV. This episode is sort of triggered by a discussion I had on YouTube with a guy. So we were out drinking beer last Thursday, a bunch of nerds, and one of them referenced seeing a video where my assembler programming video was referenced. So I had to look at that, and it was from a Kiwi guy called Not a Wizard. So I watched that, and he seems to be skipping all of my sort of education and just focusing on the last few minutes where I did a few of the VIC tricks, just, I mean, to show that what you could do. And that was sort of his focus, and I concluded that there might be a need for like a VIC education thing. So I've spent a fairly substantial number of hours documenting a number, or basically the inner workings of the VIC, and also a number of the more commonly known VIC tricks. Most of these were invented back in the 80s, but so the modern stuff is not really covered because I'm not a demo coder, so I don't know them. So and these are sort of the ones I know, and most of them I understand, and there will be ones I only sort of barely understand, and it might be that my explanation might not be totally perfect for you, but at least it gives you something to dig around and see if you can understand it more. So over to programming the VIC. Okay, so welcome to the crash course. Let's see how crash it will be and how much coarse it will be. So VIC is the chip inside the C64 that generates the graphics, and basically any of its registered is affecting something that has to do with the visual output of the C64. So the basic modes it can work with are high-res and multicolor. So that's sort of the color mode. And then the kind of technical mode is the character mode or a bitmap mode. There is also something called extended color mode, or we will have a slight look at that one as well. But that is just a variant of a character mode that has sort of additional functionality to it. So high-res is 320 times 200 pixel. That is the actual screen. But when you use multicolor mode, 2 pixels are used to give a pattern that could be either 00, 01, 10, or 11. So it gives 4 variants of a bit pattern, and that determines color in those instances. So that means that you need 2 bits to determine the size of a pixel. So the pixel isn't like the normal little one, it becomes a wider one. And the screen you see here, that's of course the standard text screen, so character mode, and it's also high-res, so it's sort of the full resolution of the C64. Character mode could be 40 times 25, and a character here is sort of a cell, or a Nintendo would call it a tile, which is 8 times 8 pixels. But again, if you go into multicolor mode, it's the same as with bitmap. You have 2 bits determining the color of a pixel, and then the pixel also becomes wider, so it's only 4 times 8 individually addressable pixels. Bitmap mode has like 3 components to it, or 2 if it's high-res and 3 if it's multicolor. There is an 8 kilobyte bitmap. Yeah, we will get to VIC bank, but just now, accept the fact that you could be either high or low in this inside the VIC bank. And then you have 1 kilobyte of color memory, which sits at the hard location at D800. So that's sort of an area inside the IO space where you put the colors. It's not actually 1 kilobyte because it's 1 kilo nibbles, because only the lowest 4 bits of the bytes of D800 are actually used. And then in multicolor mode, there is also the option of having a 1 kilobyte of screen memory, which is the normal screen as you would see in, and you define it basically the way you do in character mode. And that one can have one of 16 different positions inside the current VIC bank. Again, we will get to VIC bank. So, and character mode is yeah, easier and trickier. So you have a 2 kilobyte font, and there are 2 like fixed locations where the VIC can see it, and that is on address 1000 and address 9000. And the tricky part here is that the CPU and the VIC does not see it on the same address. So if you take the CPU and want to kind of see what's in address 1000, it will be what's in RAM. It will not see the content of the system font there. So if you want to see the system font, you need to set address 01, the bank switch register, to 33, and then you can see the actual font on D1000, and then you can copy it out and manipulate it if you want to do that. So if you see a number of like early crack intros, they had the ambition of being really, really small. And for that, they took the original font and then made some like mathematical manipulation of it. Then you didn't need to include a font that added to the weight of the intro, which is a smart way of making things a little bit smaller and reuse the graphics that's already provided for you. Okay, so that is the font. And then you also have 1 kilobyte of screen memory. That's always there. And the 1 kilobyte or kilo nibble of color memory on D800. And just to give you a brief understanding of how this then works. In high-res mode, you have the pixel set in the font. So if the pixel is 1, it picks the color that it finds in D800, and then it picks the background, the zeros, from D021, the background color. That means that in every like 8 times 8 cell, a character, you can only have 1 foreground color and 1 background color. But then you can have a new foreground color in the next character, because that is what's in D800. In multicolor mode, it's this messy thing with 2 bits determining the color. So if you have 00, it picks from the background, so DO21, and then 01 is from DO22, and 10 is from DO23, and then 11 is from D800. So what you see here is that you have 1 color, the DO21, which is common for all of the screen. Then you have DO22, which is unique for, which is also common for all of the screen. And then DO23, also common for all of the screen. And then you have D800, which is individual for that 8 times 8 pixel cell, or 4 times 8 as it becomes now. Extended color mode is that's a tricky one. So the pixel color is in D800, yeah, basically like normal. And then so this is high res. Think of it like high res with extended opportunity of setting the background color. So it uses bit 6 and bit 7 of the character to determine one of the 4 background colors. So you can set 4 background colors. They are common for all of the screen, and they are picked from DO21, from DO22, 23, and 24. Yeah, and DO21 as well. So it's all there in text. The text might explain it better than I do. Is there any real use for extended color mode? Yeah, possibly. I mean, it's only up to your imagination if it's usable or not. The additional thing which makes VIC really, really cool is the function of sprites. So these are independently addressable graphical objects that you can move around totally freely. There are 8 of them, and you don't need to take sort of... If you have software sprites, you need to kind of place the content of that object into the bitmap, and then when you move it, you need to move back the original, what's supposed to be underneath, and then you move the sprite and place it somewhere else. Here you can just move it around. It's not messing with the underlying characters of bitmap. It's totally independent. And like the color modes of the screen, these come in a high-res version and a multicolor version, and they work basically the same as the rest of the VIC for that. So 24, so 3 bytes, 1 byte is 8 bits, so 24 bits times 21. And why 21? That seems totally logical. Well, it doesn't, because this is 3F, so 63 bytes, and 63 bytes is sort of what you can fit inside a 64-byte instance. So a slot for a sprite is 64 bytes, but only 63 of them are actually used for sprite content. You could store an individual color there just so you have it stored next to the sprite, but it's a free byte, that one. And of course, in multicolor, it's the same, that 2 bits form a reference to a color, so the efficient size of, or addressable number of pixels is then 12 times 21. Sprites, they also have a number of registers where you can manipulate them, and one of the things that is really handy is you can have them expanded or not, which means that they are twice as wide or twice as high. It's individually settable if you want to expand them in X or Y direction. Okay, and interrupts is also an important part, and there are multiple sources of interrupts in the C64. The timer, and you have NMIs, and several other like sources. And we will not go into the NMIs or anything timer related. These are only the interrupts that come from VIC itself. So and an interrupt is, normally you have the process running, and then suddenly you have something triggering an interrupt. The processor halts what it's currently doing, and it's looking at a vector for triggering interrupt, and then it's servicing that interrupt, and then getting back to what he was doing before, continuing to doing that. And that is a super handy way. And basically, if you write any sort of program on the C64, there needs to be sort of an interrupt. There is already like a standard interrupt running in the machine when you're running it, like when you're just booting it on. That is a timer interrupt that has a certain frequency and that interrupt is servicing stuff like scanning the keyboard is a major thing that it needs to do on a regular basis, because yeah, you could not just check keyboard any other way, I would say. So and the key sources for VIC interrupt is a raster interrupt. That is when the screen is painting a particular line. So if you set the interrupt to one particular line, when the beam is painting that start painting that row, then that interrupt is triggered. I would say there is no demo that is running without the raster interrupt triggering at some point in time. One thing which is more like game oriented is a sprite collision, and you could have sprite collisions when the sprite collision is colliding with another sprite, and it's also when the sprite is colliding with the background. two sources, and then it has something to do with light pen as well. I've never used that, so I wouldn't know, but of course it's possible to have a trigger, a light pen, a light pen touching the screen. Okay, so what I was referring to earlier is yeah, so the screen is painted from the top left corner, row by row, and think of it like a printer. Yeah, people don't have printers anymore, but a dot matrix printer where the head is sort of bzzzt, bzzzt, bzzzt. So printing every line. So think of a dot matrix printer here again. When it finishes the end of the screen, it's starting on the next row, and that is that is called a horizontal blank, when sort of the beam is turning off, moving to the start, and then starting to print again. And then when it's printed all of the screen until the very last line, you have a vertical blank. And that is when it's sort of in the lower right corner, and it's turning off and moving to the first, starting the new page, if we go with the dot matrix analogy here again. Yeah, so VIC registers. We will now go through a number of the VIC register, just to give you a basic background of what they are doing, to give you a flavor of what the VIC can actually do. And in the second part of this, we will look at a number of VIC effects. And but understanding the VIC effects sort of assumes that you have been paying attention to this. So do pay attention to this. First of all the VIC registers sit inside the area D1000 to D02E, except this one, because the C64 has 64K of memory, and as we have been discussing in multiple other episodes, address 01 tells the bank configuration. If you would see RAM or ROM here, or if you would see RAM inside the IO area, you can see the IO registers such as the VIC, or you can see RAM, or you can actually flip in the characters, as we discussed in one of the previous slides. But the VIC can only see 16 kilobytes, so that means that there needs to be a register that sets that can have like 4 values to set that 16K to be the bank 0, 1, 2, or 3. And those are the lower 2 bits of address DD00. So it's in the second CIA chip, the second timer chip has this. And to be honest, it's not a really good place to place it, because you also have the communication with the serial bus here, which means that yeah, when you're starting to read and write stuff from the serial bus, unless you really take care of which VIC bank you're in, you can mess things up really badly. So bit 0 and 1 sets the VIC bank here. The really awkward thing is that bank 0, the one from 0 to 3FFF, sets 1 in DD00. So for selecting bank 0, you actually set the value to 3, which doesn't make sense, but that's how it works. Okay, one of the absolute key register is D012. That is the raster pointer. When you read it, you are reading the current line that the beam is painting for you, which line on the paper the dot matrix printer is printing. And when you write to it, you are setting the value where you want a raster interrupt to trigger. You need to do a little bit more to set the raster interrupt, but in order to kind of determine where you want it to happen, then you need to set D012. D011 is one of the other really important, and it has multiple functions. So first of all, smooth scroll. That is sort of moving, and I should do it like this now. So this is moving in Y direction, and just by setting those 3 bits, you can have like 8 different positions. And then you can also set 24 and 25 row text display. And why would you want 24? Why don't you always want 25? Well, in combination, if you have 25 and you smooth scroll, the entire visible screen area will be moving up and down. Whereas if you set it to 24, the movement will be inside that hidden 25th line, which makes it really, if you want, then you can smoothly scroll up and down without moving the entire screen, the edges of the screen as well. Yeah, you can blank the screen, and this is also bit 5 is where you set bitmap mode. Normally when you set it to 0, it's character mode then. And then there is this bit 6, which has this extended color text mode. Well, the one I call extended color mode before. Yeah, and the other thing is the dot matrix printer printing the screen. DO12 can only hold addresses up to 256 because it's a byte, but there are actually more lines than the 256. So there needs to be some sort of extra bit to tell if it's passing into like row hex 100 up until when all the lines are there. So this is so you basically also need to set the DO11 if you want to set the raster interrupt. So again, writing to that bit will set the high bit, and it's 0 by default. So if you don't set it, you will only be able to set the raster interrupt colliding with one of the first 256 lines. Okay, so DO16, excuse me, that's smooth scroll in the X direction, so like that. And the same here as with the 24 and 25 row mode. There is a 38 and 40 column text mode. Again, you have this scrolling 8 bits, and then you move the border in, and then all scrolling takes place behind the edges of the border on the 64 screen. Multicolor mode is also here, so if you would like to enable the multicolor mode, then this is bit 4 here. Bit 5, to be honest, I don't really know what that is doing. Stop VIC, no video output, no RAM refresh, no bus access. Yeah, I don't think I've used that, and it's possibly that one is important for a number of VIC effects. I just don't know it. Okay, colors, you've already seen them referenced in the previous slides, but the DO20 is the border color, the border around. DO21 is the background color, and then 22, 23, and 24 are used in different contexts depending on the mode you're using, and we've already seen that done. So yeah, just a list of them. Sprites, they have many registered assigned to them. So first one is D1000 to DO10. Here you have an X and Y position of each of the sprite because you can set them individually. And then again, since sprites can be set in the X direction into more than position 256, again you need an extra bit to tell if you want to set it to address 100 and beyond. One would think that there would be a need for also having like a most significant bit for the Y position, but that doesn't really happen. To the best of my understanding, the sprite basically appears both. If you set it to like 10, it would appear on address 10, but it would also appear on address 110. Because if you set the sprite and you move it down, it appears as a ghost on the very top as well. But normally for the C64, this isn't a problem because those areas are covered with the border anyway. It will only be visible if you actually open the border and reveal what's underneath. Okay, so DO17 is expanding the sprite in Y direction and DO1D in X direction. And why don't they put all the register related to sprites like next to each other? They didn't, so just live with it. Sprite to sprite collision and then sprite to background collision. So, and if you have 3 sprites colliding, the corresponding bit of all 3 of them would be set. So, or let's start with this simple case. Sprite 0 and sprite 1 is colliding. The bits on both sprites 0 and 1 are set. But if you have sprite 0 and 1 colliding, and then you have sprite 6 and 7 colliding, the 4 bits are set, and you couldn't tell which one collided with which one. For that, you need additional logic. All the register is telling you this sprite was hit by another sprite. Now you find out what really happened and how you would like to act on that. And the same with sprite to background collision. To be honest, sprite to sprite is usable normally, but sprite to background, that's less used in games, because in order to have that usable, you basically need a blank background, and only when you hit like a wall would you react to this. But if you look at the modern game, there are rarely like black areas of background where your little main character is moving. There is typically graphics there as well. So, and then it will be colliding always with the background. So it doesn't really make sense. I know that there are use cases for this, and one of the really complex sprite crunching articles on the internet by Linus Åkesson, LFT, he's using this for his super cool sprite cruncher. And but you will have to listen to Linus explaining it himself in the interview, episode 59, no, 60, yeah, something like that. Okay. And then of course every sprite has their individual color. You would have them from DO27 up to DO2E. Okay, and more on sprites, and sprites are really fun. So the whole thing around VIC is that when the beam is painting the screen, if you are changing values on the screen, like the DO11 and DO16, depending on the exact cycle you are poking, you can provoke the VIC to do things it didn't expect that it was supposed to do. And we will get to what happens there with sprites. But first the positioning of sprites, because there was nothing in the currently discussed that was pointing to where do I find the actual sprite data. And this is sort of the most complex part about sprites. So you have a 16 kilobyte of VIC space, and then you placed a screen on that using DO18. The screens can sit on like 0400 even addresses, but a screen itself is only 1000 bytes, 40 times 25, and expressed in hexadecimal, that's 03E8. That means that basically from 03E8 until 03FF, you have a little empty space. And the VIC uses the last of those 8 bytes to set sprite pointers. So those sprite pointers could be 100 to, it has to be FFF, right? It could be, could there be 256 sprites inside a bank? I should be able to compute that, but I didn't prepare that. But so at least you set the relevant pointer to which of the sprite positions inside the VIC bank where you could find the sprite data. So in the normal case, the screen sits at 0400 when you boot it on. That means that the sprite, the pointer to sprite data sits on 07F8 for sprite 0, and then onwards for the rest of the sprite. I hope that was understandable. I think I went through a bit of that. So where do I place the sprites? Yeah, there is a little character buffer. So if you, tape buffer on 0340. So if you don't have any other place, then that might be a good place if you're only having like a few sprites and you're using bank 0. We're not going to go deeper into that, how you place sort of memory management of your projects. This is just for the VIC. Memory management would be for another episode, I guess. Okay, so once you've started painting a sprite, you cannot say, skip it. I've drawn 3 lines. I don't want any more of that sprite visible on the screen. I'll DO15, I think it is, that turned the sprite off. I'm turning the sprite off. It will have no effect. It will still paint the entire sprite. Okay. So you can change the X position of the sprite, which means that you can make it like by changing the X position on every line, you can make nice curvy wobbly things, but you cannot move it down or up. Again, that would be, if you could move it down or up, it would be an option to reduce the size of the sprite or prolong it. Again, there will be tricks for that on how you do that, but you cannot do it by just setting a register easily. You can change priorities between sprites and background and sprite and so if you have a sprite that goes from one edge of the screen, you can set priority to lower than you can have it higher than graphics and then set it to lower and then to higher again. So it could go like behind something in the middle if you want to. And you can change the colors. So if you look at a number of the things that happen in demos is that they are doing splits, and that means that you are making like a color bar which starts at one point and stops at another point, and then like another segment of the color bar appears. And you can do that also sort of for the color inside sprite. So if you have a sprite and you change the color in the middle, it will have different colors depending on where you place it. And yeah, and I'm not going through what you can change in sort of in the X direction and in the Y direction. Some of the things will only work if you set it, and then the next row it will be apparent what you actually did. But colors, for instance, you can change it like that. I'm not really sure a priority. It might be that you can only do prioritization in that direction. Yeah, well, I should have checked that. I didn't do that. Sorry about that. So, but one of the things you can actually change is, and I think that only works sort of on a row per row basis, is changing a multicolor sprite to a high-res sprite and then changing it to multicolor sprite, so you can have like a middle segment of a sprite that is high-res. Not really sure where you would use that, but I think that it's possible. I used to write for the computer magazine Data Magazine in Sweden. No, it's not called Data Magasinet, you stupid people. It's called Dator Magazine. Okay? There is a scan of that available. It's called DMZ Archive or Arkivet. I wrote an article on sprites in 1991, issue number 14. So if you are Swedish speaking and you would like to read that, that's where you find that article. Okay, and the last piece, which is sort of very un-VIC related and something they kind of stuffed into VIC for some unapparent reason. Normally when you scan the keyboard of a C64, it's a matrix of 8 times 8 characters, and that is in CIA, timer chip number A. But in order to extend that for the 128, they added bit 0, 1, and 2 inside for the additional keys on the 128, the numeric keyboard, and it has a number of like extra keys compared to the normal C64. Yeah, it's really weird that VIC is involved in that because it has absolutely nothing to do with VIC. it's like changing the bank for VIC in in a timer chip as well. And here, so you're controlling the VIC from the timer chip, and then you're controlling what should be the timer chip here from the from the VIC. Really weird. And then you have this magical register DO30, and that one turns on 30, or it has a bit that can turn on 2 megahertz mode inside the C64. So if you're running C64 mode on 128, you can use this to add to run 2 megahertz inside the 64. Which is really handy for stuff that is time critical and where you want sort of the computer to work. One of the cases where this was very much used was when you were crunching. So analyzing the content of a program and then trying to use an algorithm to represent it in a smaller way. You know, the flashing borders when you start the program, that is when it's decrunching. It takes the compressed data and then sort of runs the reverse of the process to inflate it back to the original form. But that was a process that could take hours and hours. Cruel crunch could take like 8, 10, 12 hours, and if it was a really big program. So if you turn off the screen, because this messes with the screen. You cannot have screen on at the same time. If you turn off the screen, you let it run in 2 megahertz mode, and when it's done, you turn the screen back on. That means you can crunch using half the time. And for releasing a crack on the 64, if you could save 4 or 5 hours just by saving crunch time, that was a big thing. So DO30 and running 128 was a cool way of saving hours to when you were competing on time with everybody else. Okay, VIC timing. So as I referenced before, the key to doing many of the VIC effects is changing a value inside the VIC at a specific place on the screen, just when it's drawing something in particular, and then you change a bit in the register and then magic happens. So you need to know exactly which character you're basically drawing. Roughly a character on the screen represents one cycle of the raster bar. So it's really key to then be able to have a stable raster. You need to know exactly which cycle you're on. And if you're setting something like a raster interrupt, they can happen within like a time frame, because if you're executing an instruction when the IRQ hit, that instruction will always be done in full before the IRQ happens. And C64 has a number of instructions that take a very different number of cycles. A NOP would take 2 cycles, but you have instructions that take up to 6 cycles. And I think if you're also extending it across a page border, there could be a few instances where it's actually taking 7 cycles. So that means that the raster interrupt starts within like a range of like plus minus 5 cycles. So whatever you need to do, if you're going to have one of those routines that's built on poking on specific value at a specific point on the screen, you need to have a stable raster. So you first need to have a mechanism to get to know exactly which cycle you're on. I'm not going to go through how you do that because there are multiple techniques of doing it, but I'm just saying that you should look at stable raster interrupts for that. There are multiple examples online already, so I'm sure you can dig that out if you only have like the pointer of stable raster. Okay, and of course you also need to know how many cycles there are per row, because otherwise you wouldn't know where you are on the screen anyway. So you need a screen map to know how many cycles you have available. And the thing is, that varies, which is adding the complexity here. First of all, it varies between PAL and NTSC, and I think there are also two variants of NTSC. So if you look at all the demos with the all very, very specific effects, they are almost all of them PAL only. You couldn't really adjust them to work on both systems. That would be too much work. It's writing the same code again. And then you have normal lines, and they are 63 cycles. And then you have the bad lines, and I'll show you a bad line. And bad lines is when the VIC takes precedence over the bus and the CPU just sits idling. It's basically halted for the period of time where the VIC is doing its thing, and then it started again. So bad lines is VIC stealing cycles from the CPU. Also sprites. So on the lines where you have sprite data, you also have the VIC stealing cycles from the CPU. Just to get to this bad line thing, and I'm not really sure I'm using the correct terms. Bad lines is what this is commonly called, so that is sort of the accepted term for this. But let's call them a character line. It's this block of 8 character or 8 raster lines that forms one character. The first line of one of those is called a bad line. That's when the pointers for the actual characters are fetched by the VIC. And then the CPU is left alone for the rest of the 7 lines. And then you have a new bad line. So line 0 and line 8 and line 16 would be the bad lines. And of course, those aren't the raster lines because DO12 starts from way up above the screen. So 30 something is the first line of the screen. And it also depending on the scroll registered in DO11. So bad lines, when the VIC steps in and takes the bus and the processor sits on the bench waiting for 40 cycles, which means that it only leaves 23 cycles for the CPU to work on that line. Okay, now we're getting to like timing charts, and they are super complex, and I'm just going to kind of step through them and show a few of the things. I'm not claiming I understand them fully myself. There are multiple sources for this. There is a paltime.txt written by a totally brilliant Finn called Marko Mäkelä. He was very, very active in the very early stages of the C64 history here. You have Christian Bauer, the coder of the Frodo emulator, which was sort of the thing before Vice. He has a timing chart, sort of a VIC article that contains timing charts. And then LFT has done his timing charts as well, and I will show examples of that. So what you will see now are extracts from the paltime.txt by Marko Mäkelä, and I will also show you briefly LFT's timing chart. And again, I don't claim I understand it at all. Okay, so in PAL, on a normal scan line, it has no sprite. So it's not a bad line, it's nothing. It's just a normal line. Here you see the number of X's, and I think my mouse pointer will be visible. Here you have the Phi2 CPU. So this is where the CPU has access to the bus. And you see from here, the X shows that the CPU has access to all 63 cycles. With sprites, there are equal signs, which means that something is happening here on a normal scan line with sprites. So the CPU does not have access to that. And then there is also capital X, which has like special conditions, bus requesting. So it seems that you can do writes there, but you cannot do reads, because then it will halt until the VIC has done its reading of the sprite pointers. That's how I read it. And then you have the bad lines, and here you see that the equal signs here show that the VIC has access to that, and the CPU just sits on the bench. And you have the small x's, and then you have the capital X's here that shows that depending on, you can do a write, but you cannot do a read in those cycles, because then the VIC will allow you to write but not to read, if that makes sense. And then you have the bad line with sprites, and here you can see that the number of cycles that the CPU actually has access to is really limited. And then there is a similar chart for overscan lines, and I'm not going to bore you with that. If you are really interested in this, eventually you will need to learn it, and then you will probably need to find the original chart. I'm sort of just showing the buffet of what you might need to know depending on what you want to code. Okay, so this is Linus Åkesson, LFT's chart. It's a massive piece of work, and yeah, it's basically showing the same thing, I guess, but in a more graphical and three-dimensional way. Okay, now we're getting into the VIC tricks here. First of all, a scroller. If you do a plain like text scroller, a row of text that rolls on the screen. First of all, you set the column to 38 columns. We are doing like, think of it like the lowest or the highest row on the screen have a very fluently floating scroller. So you have the smooth scroll register here in DO16, and let's assume that one is 7, and then you set it to 6, and you wait until the next screen, and then it's 5, and then you wait to the next screen, all the way down to 0. And then the next screen, you cannot go lower than 0. Then you needed to set it to 7, and then you need to move all the characters one step to the left. And then you do a loop such as this one, LDX 0. You load accumulator from address 0401. So that would be the not the first character, but the one after the first, and then you move that to the first character. And then you do that for all the characters on the screen. That would be comparing with 27, hex 27, and because we started on, yeah, this, you might just need to do 26. Yeah, I didn't compile this. I just wrote it like that. It might be that you needed to do only you need to compare with 26. Yeah, whatever, sorry. A core scroll, you move all the characters, and then you set the scroll register to 7 again, and then per screen you go down to 0, and then when it's going beyond 0 you set it to 7, and you do this again. So it's moving the entire set of characters one step. And if you look at changing DO16 register, that takes only a few cycles to the smooth scroll, just moving it one pixel. But this one, of course, takes more. So that's sort of the issue when you're doing a number of things. In some of the screens, what you're doing takes very little, but sometimes it takes a lot. And when you have a lot of things that takes a lot of time, you run out of CPU time. And if you look at what's difficult for a demo coder, it's the constraint of 64 kilobytes. You cannot, and the number of cycles. So the thing you can actually do is the other thing that's complex. Normally, you can sort of compensate if you have few cycles with using more space. Tricks like loop unrolling. Here I have a loop. But on every lap, that one increases X and then compares X and then moves up again. But you could have LDA, STA, LDA, STA. So you generate an unrolled set of instruction. That will be bigger, but it will be faster. So it's the trade-off between a very constrained area of memory and a very constrained number of cycles per screen that you can use, and those you need to juggle and balance and find the best spot. So it fits inside the available RAM, but it also runs as fast as possible, so the effect is as fast as possible. A sprite scroller is an easy thing. You can do it two ways. Otherwise, first the option would be to set a character or have a sprite that has sort of the shape of a character, and you set it, and then you roll that as you would do if in a game where you move the main character like that. But the other, like, more common way of doing it, or at least a very common way of doing it, is setting a mat of sprites and then shifting the content of it. So the sprites don't move. You just move the content inside the sprite. There will be examples. I'm just going through a number of things here, and then we will get to examples, because some of them are combining a number of the effects we are talking about here. Okay, so how do you open the border, upper and lower? This was for me the first jaw-breaking thing I saw on the 64. The border was there. It was absolutely impossible to change it or move it or do anything with it. And then suddenly somebody opened it. How could they possibly remove the border? It was implemented inside the VIC by the engineers of Commodore to be there. It cannot be removed. Yes, it could. So the trick is you set 25 rows as we have here, and the raster is printing, and when it reaches beyond line 24, so into line 25, so this is row 25, raster is painting here, and it's suddenly here, and then you set it to 24 character modes. That means that the 25th row is not there anymore, and the raster is painting that row, which means that it will never reach the end of the screen, because we moved the end of the screen to before it was, but it would still be in the mode where it's drawing screen. So it's drawing and drawing and drawing, and then when it's going beyond 25, you turn on 25 again, because you need to set it up for 25. So when the next lap happens, so the next screen happens, the screen is prepared to be in 24 character modes, being ready to move to 24, and then 25 again. And the precision here is, you don't need very much precision here. The only thing you need a precision for is you risk having flickering if you're doing this setting to 24 mode. So you might want to be a bit more precise if you want to draw most of line 25, and then you do the flip, and there will be no flipping or visual artifacts on the screen, because of course those you also want to avoid in a nice looking demo. You cannot like do your trick but it looks like crap because something is flickering. Bugger. I was just clearing my throat, had a bit of coffee, and the ambition was to pause the recording before I did that, so but I pressed stop, and then I spent the next section just talking to myself rather than recording. So I would need to record it all for you again. So that's the way it is. So we had gone through the opening the border of the upper and lower. Now we're going through the side border thing. The technique is absolutely the same. When you do it in the Y direction, you are setting DO11 to 24 lines or in 25 lines. What you do here is in the X direction, and you set the DO16 flag for toggling between 40 column mode and 38 column mode. So just the way it did before, you are printing the beam is there, and it's printing the screen, and it's entering the area of the last column, and then you shrink it to 38 column, and that means that the beam never hits the position where it kind of collides with the border, and then you increase it back to 40 column mode, but the beam is already like past that and it's still thinking I'm not going to paint any border. And the cool thing here is that you can combine those two effects to have a screen which is basically borderless. If you also combine it with a sprite multiplexer, you are painting all the sprites, and then you move them to a new matte, and then a new matte, and a new matte, and then you can have a big matrix of sprites covering the entire screen. And that particular effect is called SCOS, made famous by the 1001 crew. Okay, so this is sort of a combination of what we talked about before. This is a demo part from Digesta, a FairLight demo from 1989, and this particular demo part is coded by Mr. Wedge. Yeah, it's Mr. Wedge. He went to be Wedge only afterwards. Okay, so here you have a matte of sprites in the lower border. The matte of sprites, it's placed there, and what Anders is doing is just shifting the content of the sprite matte. So it's in the lower border, but it's also in the side border, so all of the lower border is open, and then he's manipulating the content of those sprites into making it the sprite scroller such as that one. And you can see it also had a bit of a fancy effect where the scroll wouldn't just be a flat scroll. You could kind of scroll segments of the scroll and all of that. But those are sort of extras on top of a standard sprite scroll, or any scroll for that matter. It would be very difficult to do that without having like shifting content. You couldn't do it using a normal character scroll. Okay, so the next one here is this one. So this one is from Per Node. I think this is from the same demo. It's also from the FairLight demo Digesta, I think. Here he uses sprites that are characters, and then he's moving the position. So this is not a matte of sprite. It's characters actually moving. Sprite characters actually moving. But please note that there is a stable raster bar in the beginning, or in the background here. And if you are working with sprites, I already said in the beginning that when sprites appear, they are stealing cycles. And if they are stealing cycles, how are you going to make stable raster bars and stable raster splits in the background? That is sort of the key trick here. Let's see the demo part here. So it's a sprite scroller. That is the effect that you are seeing here. But do remember this combination too, because we will talk about DO17 in a minute, and the sprite extender, which explains how he does this. Oh, okay, so what you see here is FLD, flexible line distance. Here you are ensuring that the DO11 register is set so that it doesn't, so the 3 lowest bit of DO11 does not compute to the same result, the same number as the lowest 3 bit of DO12, because that's when a bad line happens. So you delay the bad lines from happening. And if you see here, you have a first line. That's actually a scroller that you can start with the joystick, but I don't have any joystick here, so I didn't do that. But and then down here, let's see if I can no, I couldn't. Oh yeah, I can do it like that. So we zoomed in a bit here. So here, around here, I am allowing again the bad line to happen, and that's when you have a new character line happening. And then I'm delaying the next line, and delaying the next line, and delaying the next line. So what happens here is that by delaying bad lines from happening, you are pushing the next line down. You're basically scrolling it down, but you're doing it in a VIC trick kind of way. So the VIC doesn't have any like content which is it's supposed to be printing in that area that opens between the visible line. It's sort of expecting that it's supposed to print the next line and print the next line and print the next line. So this is where like an awkward thing happens. And the byte you see there in the background, which says FairLight the Magicians, I believe I printed there. That is the byte from the very last byte of the current VIC bank. So if you're using bank 0, so from 0 to 3FFF, it's the byte 3FFF. But if you pick another bank, it would be the last of that bank. So it's not 3FFF always, it's 3FFF if you're using bank 0. So by updating 3FFF on every row, you can print graphics in the background like I did here. Right, and that was actually my code, and this is also from Digesta, I think. Sprite multiplexer is, so when you draw a sprite, once you started painting it, it's there and it will paint for the entire sprite. I'm saying that, and then of course there will be an exception to the rule in the very end of the presentation, but for now let's assume that that is what happens. So you can move it in the X direction, but you cannot move it in the Y direction. But once you've drawn the last line, that hardware sprite is free to use again. So you can just change the Y position and then you can make it appear again lower in the screen. And if you make that in a smart way and you have a table that you copy to the sprite register and you sort the sprites so that they are in sort of in the logical order, you can show the first 8 and then you could show the next 8 and then the next 8 until the screen is done. Let's see how that looks. This was also FLD down there, so it's a combination of a sprite multiplexer with the with a bit of FLD. This is Peter Aldenius, judge, coding this. Very nice logo by The Hobbit, and the music is the same as you heard before in my part, I think, by Mr. Wedge. So he's also the one doing that. Yeah, you already heard that. So DO17 stretcher. There are multiple ways we can do DO7, and we will get to Sprite Crunch in a minute, but the DO17 stretcher is sort of the easy way to do things here. When you are on a row, you can set expand sprites, and then you put them back to not being expanded. That way you would have the current row printed again in the next row. And then if you repeat that on every row, you would have the very same line of a sprite stretching all across. So basically you can just print the first line of the sprite and you would have that line be on all the lines of the screen. The good thing is, if you want to roll the content and if you want to make some sort of animation, you only have the 3 bytes to manipulate, and it will show all across the screen. So you don't need to shift a long row of sprite contents. You just shift once in one row. The good thing with this is also that this uses the same number of cycles. You are stretching the same sprite, so that sprite always steals the same number of cycles. It's the same sprite, and it takes the number of cycles already. Let's say it takes 2 cycles, and then so that becomes a fixed number of cycles that the sprite is stealing, which makes it really predictable, which makes the loop you're doing also very predictable, because you know how many cycles the sprites are stealing. And now we can get back to the combination 2, the code by Pernod, where he had the characters, the character sprites going up and down. He is using this trick. So he has a DO17 extending a blank line in the beginning, just to ensure that the sprites are stealing the 2 cycles or whatever he needs to make his rasters absolutely stable. and predictable. So he doesn't need to kind of worry about the sprites. He only needs to worry about when to not extend that sprite with DO17 for the duration of the character height. And then when you reach the sort of end, there is also a blank line that he keeps extending until the very end. So that effect is actually showing an extended blank line, and then the character, and then an extended blank line, and then he just rubbers that character within when he's showing the character and when he's extending the blank lines. But let's see this one. It's a rather simple thing. It's not that much code to do it, but I still like this a lot. I wrote an article on this in Data Magazine, and I think this one, for those of you who read Swedish and want to see the code behind this, it's in DMZ-arkivet 1991, and I think this is in episode or issue 15 or 16 or something like that. But this particular effect is coded by Kjell Eriksson, chair of SSS, who then became chair of SuperSwaps of Horizon. And degkrok, yeah, that's a Swedish term. When you're making dough, you have this machine, and then you have like an instrument that to the machine that blends your flour and yeast and water or milk or whatever you're having. And they are sort of shaped like that, that instrument that sits inside the machine. So that's why I call it degkrok. Okay, and now we're watching a combination of a few of the effects here, because that is sort of the thing. What you want to achieve is some sort of impression. You're not showing off that you know a certain effect. You want to show something that looks nice, and you use the effect as a tool to achieve that. One of my favorite demos, Think Twice Won by the judges. So FLD introducing the first screen here. And this is ESCOS. So this is opening the upper and lower border, but also the side border, and then covering it with a sprite mat, and then producing a scroller inside that sprite area. My mind was blown when I saw that. I had Greyhawk showing it to me, and he was fiddling with his antenna cable because he was using a TV, and I was absolutely sure that he pulled out the video cable just to fuck with me. He did fuck with me, because I totally thought, I was absolutely convinced that he messed with the video cable before I saw the scroller, and he was laughing so hard that he managed to fool me. Okay, so this one is by White of the judges, and I should also mention, I think it's Red doing the music. That's the only pity about this. The intro there interrupts the intro music by Red, and that piece of music is absolutely great. Okay, now VSP, variable screen position. If you create a bad line condition within cycles 15 to 53 by setting DO11 so that the lowest 3 bits of DO11 is the same as the 3 bits of DO12, then the VIC sees that, oh my god, I need to set this to a bad line. And then it sets it to a bad line, reading the pointers, the character pointers, and updating everything. But then it's not starting at the start of the row. It's starting that in a later position of a row. So what actually happens is that it starts writing the character row a bit into the screen, and then it writes it, and then it wraps around so that basically on the next character row is the end of what should be the first part of. So the first part of row 2 is what is actually like the end of row 1 if you didn't apply the trick. So the screen start is sort of delayed. I think that sort of describes it better than I did. And it's inserting dummy characters. So you see this this check mark little thing in the beginning here on the screen let's see if I can zoom into that one. So I think this is the pattern it inserts, and I'm not really sure where it fetches that from. It could be that this is also 3FFF, but normally I think it's sort of that check mark. Yeah, whatever. So the actual content is wrapping around, starting from the next line, and then so you can actually use this trick to course scroll the entire screen with only a few instructions. So it takes a few raster lines and you've scrolled an entire bitmap screen around. And if you do that, you need to update only like one column of the bitmap to scroll it fully, and that's for sure something you can do within the cycles you have during one frame. Whereas moving an entire bitmap in one frame, you couldn't do. That's absolutely impossible. It takes way too many cycles to do. So this is making it possible to do things that you couldn't do using like raw CPU power. However, there are side effects to this trick. On some machines, in some instances, it starts corrupting the memory. The VIC starts trashing memory addresses ending with 7 and F. And if you have something important there, which you presumably have, then you would have the routine. Trashing your memory, trashing your graphics, trashing your music and all of that. We did have an interview with LFT. I think that's episode 59, or yeah, I think it's 59, where he talks about VSP in general, and I recommend you to have a look at episode 59, especially where he talks about VSP, because that is sort of LFT's first claim to fame. He was the first one to sort of describe it in a coherent way, I would say. Okay. So it's sort of not advised to use it. You can still, but you have to know that it could mess up, and ensure that you only run it on computers that can actually handle it. The next thing is line crunching, and I don't really have a demo for this, and there is no visibility here, but you will see a combined effect where line crunching is also used. So you are also here fiddling with DO11. So, and what you're basically doing is you are crunching the entire character row into one pixel row. So you basically forced it to do a new bad line on the next pixel line. And if you do that, then you crunch that one down to only one pixel line, and then you can make the entire screen scroll upwards by sort of crushing the top part using this line crunch thing. What you normally do, one option is, of course, that you want it to be visually crunched and you want to see the pixels there. But if you have the screen starting with blank spaces, then you can set the kind of the scroll by selecting the number of rows you are crunching, which gives you full flexibility of like positioning of a screen. Okay, and if you combine VSP with line crunch, you get something called any given screen position, AGSP, and this is the first instance where we've seen this. So this is Bonanza by MDT. MDT is Exilon and Boogaloo, who will later join Horizon. Jörgen and Linus. And if you saw episode 40 where I was showing a few of my favorite demos, this is surely one of my favorite demos as well, because this was jaw-breaking at the time, and it's still super nice. It's still one of the better demos, especially for its time. It was absolutely revolutionizing the demo coding. Okay, we're getting into where I'm sort of on deep water here. It's sprite crunch. So let me try to explain this the way I understand it. A sprite, we've already defined it as this 24 bits and then wide and then 21 rows high, lines high. And we've already discussed that you cannot sort of, once the sprite started painting, you cannot control it. You can extend it using DO17, but there is actually a way to make it shrink as well. There is an internal pointer or counter in the VIC for every sprite. It counts sort of where in the sprite data it is going to fetch the next row of sprite data. So it starts by 0 and then it's adding 3, so it starts by 3. So it has this, you know, the sprite pointer at the end of the screen memory, and then it adds that. Then it knows where it's going to read the data from the memory. But there is a trick using DO17, which is totally incomprehensible. Only LFT actually knows how to use this properly. And you can make it go like back and forth, and but it's not fully flexible. You cannot just use it because the number of bytes that are reduced or incremented in this internal pointer is according to a pattern which is very difficult to read. I don't have that pattern here, but if you look at Linus Åkesson's page, he explains it probably better than I could, but then he explains the general line crunch, and then he adds his Lunatico piece of code where he also added 3 additional inventions to make something which is incomprehensible but super cool. Yeah, let's see how this looks. So per node here, and it's very visible that this is per node because the logo says so on the top. So this is a chunk of sprites, and so this is from the demo Rutig Banan, another FairLight demo. And to be honest, I hope this is the right demo part, because this is the one that looks like a sprite cruncher, because this is a block of sprites and I think he's crunching them. So this is the first time sprite crunching was actually used, according to most of the online references. You have to read more on this if you want to use it, because I will not be able to explain it any better to you. I'm sorry about that. Okay, we're getting into the very, very last points here. But so FLI, flexible line interlace. As we already discussed on bitmap, you have your screen, and there are a number of colors accessible inside each of the cells, each of the characters, and they are defined by the color memory, the background color, and also the screen memory. But so the background color so the background color is consistent throughout the screen. You cannot change that, or you can change it using a raster, but normally in the normal bitmap mode you cannot change it. If you add, then you have 2 colors in DO18 in the screen memory for multicolor, the low nibble and the high nibble of the screen memory. And they are individual for that 8x8 cell, or 4x8 because it's multicolor. If you can provoke the VIC to read a new screen memory on every raster row, that means that you have the 2 colors that were common for the cell now becomes per row. You can select 2 new colors per row. Showing an FLI takes all the raster time, basically while you're displaying it, but it gives you a lot more colors. So you have in a bank, you need like a full VIC bank for this. 8K is used for the bitmap, and then you have 8K 1K banks for screen, and that is the full 16K bank, so you cannot use it for anything else. But you still now have the availability of a common background color, an individual color for the D800 that will be common for the entire cell, and then you have 2 individual colors that are for the per line of the cell. And the flexibility of that compared to normal multicolor mode is immense. Most graphicians don't really use this anymore because it takes so much CPU time to show it, and graphicians have become more skilled kind of working around with the limitation and still provide stunning results. But of course, using FLI, you can provide even more stunning results because you have the added flexibility of basically more colors without any color clashes inside a cell. But you are provoking a new screen memory on every row. So you have screen 0 on row 0, screen 1 on row 1, and so on. So that's the way you do it. But and of course the files are rather big because you have the full 8K of bitmap, and then you have like full 8K of screen memory as well. Still, if the result is worth it, then and you have space in your memory and you have CPU time to show it, then why not? Talking about like video formats in general, FLI is sort of one VIC trick to add more colors into the picture. But other options would be to have sprites. You add sprites to places in the picture where you need where you have color clashes because you don't have enough addressable pictures. You want to add another color, but you don't have any color available there. Then you could just add a sprite that has that particular color, and then you suddenly have a higher resolution adding to that particular point on the drawing. But if you have a multicolor picture, you can also add sprites. You can have high-res sprites, so you can have like full resolution in parts which is done by the sprites. This is basically the same as been done in multiple games where you have a multicolor sprite and then you have a high-res sprite that sits on top of it. So you have an outline in the high-res sprite that covers the relevant portions of the underlying multicolor sprite, and then you have like full colors and full resolution out of the combination of the two. Interlace would be if you have 2 pictures and then you flip between them. It's a bit flickery, I would say, but the visual impression is that a pixel has the color which is sort of a combination of the color that is in picture 1 and picture 2. So even if it's flickering, you are giving the perception that the machine is able to generate a whole range or a whole palette which is much wider than the original 16 colors. So FLI is setting that. There is also a high-res version called FLI. Yeah, we're not going to go through that. You can have pictures FLI, and you also set the background color on each row, which means that what used to be the fixed line, a fixed color for the entire screen, the DO21, you can change that per row, so you have individual row, individual coloring of that. So that becomes an individual color as well. What you also have is sprites on the edges, and also changing the background colors on the edges. If you saw my interview with the Chaos engineer, he has been producing a tool which extends the colors from the pictures into the border, and you have one color on the right and one color on the left. So that makes the picture look like consume the entire width of the screen, which is the same as opening the border and placing sprites there. So that was everything for the kind of different video formats that are achievable on the C64, and yeah, there is a reference to an article on Codebase in the description down below that shows a number of the file formats. First of all, you of course you have the actual file formats of a number of paint programs where they have, which basically tells you where it has the bitmap, where it has the color, and where it has the screen. And the color you need to copy to D800 yourself in order to show that. So that's sort of one file format setup. But the other one would be all those FLI and NyFLI and AFLI and all the alternatives. I'm not saying, well, I shouldn't say all, but a great number of the available options. And you are free to invent your own, of course. I mean, it's all up for grabs. If you find another way of presenting graphics in a combination of DO20 splits and multicolor bitmap with sprites and what have you not, and enforcing a new pointer of a screen code or a new screen using DO11 tricks, that's one of the things that you could do. It's just do it. All right. That was actually everything I had. The last slide here is just a list of sources or possibly resources I would like to share with you. Linus Åkesson programming VIC timing. That was the VIC timing thing that I had in one of the pictures before. It's just that you have access to it so that you can see it. Dust Layer, it's a 10-12-year-old set of web pages where you can see the inner workings of VIC 2. I hadn't seen that one before, but when I started Googling on extended color mode just to make sure that my general understanding was correct, that's where I ended up. And to be honest, he has done a great piece of work there to kind of describe the VIC. So if you would like that as an alternative to reference to my reference here, I would suggest you actually take a look at that one to see if that one explains it better than I could, and you can compare what he says and what I have said here, if you can kind of get to a general understanding having those two kind of completing sources. Codebase 64 is the general go-to place for C64 code. It has code snippets for a number of things, and they are really handy. So if you want to implement something in code, but you're not sure how to do it, you could be inspired by having a look at something that is there. And that is the reference to the first one here is the graphics file specification. That is what I said on the previous slide on the number of or sort of the location for the bitmap and the character ROM and the screen and the color ROM and what have you not. All the sort of definitions of existing file formats, but also sort of definitions of the FLIs and the new FLIs and the A-FLIs and what have you not. Antimon code Linus. So Linus is Linus Puterman of FairLight. He wrote an absolutely amazing piece of text on coding demos on the C64. It takes you from the very start into all the effects, and I've been able to cross-reference a bit of what he has been writing with what I've said here, so I hope it's all consistent. But if you are kind of green on this, I would urge you to take a look at that one, because it's greatly written as well. The Dreams, this AAY, it's all about your Commodore 64. Ninja of the Dreams is one of those whiz kids doing super complex stuff. He's been kind of the father of a few inventions that are really impressing. His stable raster thing is super cool, and the All About Your Commodore 64 is a collection of all the addresses and what they are doing and all of that. So when you have seen the description of all the addresses here on the previous part of the slides, I have been cutting from basically that presentation. It's the same material. It's not from that particular source, but the same material is published in other places. And I have a Windows help file where this is implemented. So that's one of the things I'm actually using for my general reference. Codebase 64, this demo programming, I think this is the same as the Linus one. It's just that it's sort of a rewrite of the original one. The demo world records and world first, that shows the effects that are available and sort of who did the most plots on the screen, and who was the first doing FLD, who was the first doing ESCOS, and all of that. Yeah, that's also a very good place to see how old few of those effects are. And if you want to take a peek on somebody else's code, if you want to see how they did it in technical practice, that's also where you have the references to that. And then you have Linus Åkesson again, so the LFT explaining a number of the demo parts of his Lunatico demo, and this MISC, where SC is sprite crunch, massive interlaced sprite crunch. Yeah, well, something like that. So his sprite crunch is not only sprite crunch, he adds like 2 layers of additional innovation on top of the original sprite crunch, where he uses the sprite collision register to actually simplify his code in a truly brilliant manner. And I would urge you also to take a look at the LFT interviews on episode 59, where he's also referencing that a bit more than what's already written in the article of his. Okay, that was everything I was presenting today. I've had some technical difficulties where OBS was freezing and me pressing stop rather than pressing pause. Yeah, so it's taken a lot longer than it should to record this. But anyway, I'm now at the end. I hope it has recorded everything, so also the last section is available to you. I'm not really sure when we are going to publish this, possibly after Christmas, but I'm recording this prior to Christmas. That's why I'm wearing this ugly shirt. So what I would like to say is thank you for watching, and this is likely the last episode of FairLight TV for this year. I don't think I will have time for doing anything more, but it's been a pleasure of serving you content, and I hope to see you also during 2023. Feel free to post suggestions for anything else you would like me to cover, and also but in return I could ask the favor of you sharing this video and also possibly liking it and commenting. That's always very nice to sort of have a bit of an interaction to see what you like and what you don't like, and any comments and remarks you might have on it. If you are actually a demo coder and know these things, it would be good if you could also kind of give pointers or references to some real hard facts, and not this cracker guy trying to pretend to be knowledgeable about demo coding. See you in 2023. Bye bye.